Yesterday, we started kinematics for real. We defined a bunch of stuff. If you didn't get any of these notes, that's because there was a bunch of you away yesterday. I think 3 of you for sure, Akash and Alexis and Lena. Don't worry, the videos are up. You can get these notes or you can take a picture of mine. I introduced to you guys the concept of a scalar and a vector. Scalars are quantities that have magnitude only. Vectors are quantities with both a magnitude and a direction. I gave some examples of both, and we started talking about position, distance, and displacement. So position was where you were relative to some zero. Your distance is how far you've traveled, the actual ground you covered to get there. Distances only ever add. And then displacements are a change in position. It doesn't care how it happened. You could take all sorts of weird paths, but all it cares about is where you were, where you are, and the straight line distance between these things. So displacement is represented by this triangle position. This is the same symbol as position had. This triangle means delta. Delta means change in, which is a final position, minus an initial position. And we were doing a couple examples of this stuff yesterday. So this is where we were at. So I had a grid here. We had 2 cars on the grid. The distance between the 2 cars is the same. Doesn't matter which way you're looking at, whether car A to B or B to A, it's still 9 kilometers. The positions of cars A and B were both relative to some zero. So 2 kilometers left, which we also called -2, because left we typically assume to be a negative direction. Car B, the position of that relative to this 0 is 7 kilometers to the right, or positive 7 kilometers. And then to find the displacement, how these things are displaced from each other, it's the position of the thing that you're looking at the end minus the position of where you would have started. So the displacement of car A measured from B, and then the displacement of B measured from car A. If you're measuring A from B, well then your final position's over here and you would have started at B. Likewise, if you're looking at the displacement of B as measured from A, then you're starting over here. You're ending over here, so this would have just been the 7 minus -2 would have given us a positive 9, or 9 kilometers to the right. So these two are opposite from each other, just because now all of a sudden the direction you're moving for displacement matters, and this is where we ended yesterday, and then the bell was going to go, so we stopped it. Were there any questions about any of this stuff? I know I didn't give you a lot of time yesterday. Were there any questions about any of this stuff, or we should just keep, or is it just new and we should just keep doing more examples of it? Lena's like, there are no questions. Well, Lena wasn't here. Well, let's keep talking about it then. There's another example of this same kind of stuff. We're going to, instead of being in 1 dimension like this thing is, just back and forth, let's look at 2 dimensions. Let's say that I decide I'm thirsty for a Slurpee and go for a walk to the 7-Eleven. We have one not far away. There's one right here on the corner. And, I mean, this is a ballpark. As you leave Abbey, you're going to go down in front of, I mean, assuming you stay on the sidewalk. It's basically a straight shot, and then it's basically a straight shot. So assuming you stay on sidewalks, this is a rough example of what you could expect to do, because, you know, safety is cool. So what is the distance traveled, assuming that this is the path I take? The distance traveled to 7-Eleven from where I am is 300 meters down this chunk of the sidewalk, plus this 150 meters down that chunk of the sidewalk, be a grand total of 450 meters traveled. But if I wanted the displacement for this thing, again, displacement is the straight line change in position from where I was to where I am now. So I was here at the front of Abbey. I am here now. So that straight line distance is going to be this. That's straight-ish. So if I want that displacement, what do I have to do? Yeah, here, Dave. I'm going to have to use the Pythagorean theorem. The reason that I want to stay on sidewalks is because if this isn't a right angle triangle, this becomes a gross mess of a problem. But I stayed on sidewalks. Oh, look, I made a right angle triangle. We can find this thing using the Pythagorean theorem. that's just going to be 150 squared plus 300 squared square rooted. And this is going to be our displacement. We can't just add or subtract like we did before, where this meant a final minus an initial position, because now all of a sudden we're off at some angle, we're in 2 dimensions, so we have to find our displacement using these right angle relationships, or these right triangle relationships. So what's the displacement, or what is my displacement if I'm now standing at the 7-Eleven? What is that value? Yeah, here it is. What do you mean approximately? Yeah, so you got some decimals there though? Yeah. Okay, so what'd you get? Give me the 2 decimal places. 0.41. Cool. And that's in kilometers. Cool. That is the magnitude of our displacement. We have been displaced I'm going to put it down here, 335.41 kilometers. Meters. Sorry, why kilometers? Because it's Tuesday morning and I screwed up. Meters. Everything else is in meters. This should be in meters too. Meters. That's the magnitude. This thing also needs a direction, though, associated with it. Based on how I've drawn this picture, we need to put some directions in here. Does anyone have any idea? I mean, yeah, let's see how good we are with this. Which way these directions are actually going here? Yeah, here, Dave. Nope. So the way this is positioned actually more like, I mean, if I'm using this in class, this is, if I want to label this thing on here, east-ish. We are east-ish. We're going to get better than that. This is east. If you're picturing it, 7-Eleven is east of Abbey. And then is it north of Abbey or south of Abbey? I mean, we could pull out a Google Maps. But if that's east, the rest of these things should be pretty straightforward. That's east, this then has to be? Nope. North. That's south, that's west. So this is east-ish, but we can do better than that. These directions are all, I mean, it's on a 360-degree plane, right? Like you've got 90 degrees measured here and here and here and here. We can do better. We can find exactly what that angle is. When we want to find a direction for a vector, in this case something like displacement, we can put this thing that we just drew, this coordinate set of arrows, right on top of where we started. That's north, that's south, east is over here, west is over here. And what we're going to do is we're going to find the angle between one of these cardinal directions and our displacement line. In this case, the easiest one to do, given the other information that we have here, is this, because we've got a triangle that goes this way, and we've got a and then the leg goes this way. So the line between north and, or the angle rather, between north and our displacement line is the one that we're going to find here. So trig wasn't on your guys' test that you just wrote, but it's going to come up here now. How do I find that angle right there? Well, that side, 150, is what side relative to this angle? It is opposite. And the 300 is adjacent. So if you recall, or if you're just learning this for the first time, because your Math 10 teacher didn't get to it, that when I've got an opposite side and an adjacent side, and the reason I'm using opposite and adjacent is because these are known values given to us in the problem. If I have opposite and I have adjacent, what I want to use is these three letters, TOA. And so then to find this thing, we're going to have the tan of our unknown angle is going to equal the opposite side over the adjacent side. So then tan of our angle is equal to 150 over 300. And to find this angle, I don't want tan of my angle. I want to use the opposite operation to move this thing over. It's like squaring and square rooting are opposite operations. Or adding and subtracting are opposite operations. I want to take the tan inverse of the other side. So theta is going to equal the tan inverse of 150 over 300. If we plug that into our calculator, it looks like this. So all of these inverse operations are above their base operation, the sine, cos, and tan operators on the calculator. So I want to go shift or second function tan with a tan inverse of 150. I think that's division over 300. And we're going to find that that's 26.5 degrees, or I'd also call it 26.6 degrees. So that's the angle on this triangle, and now we're going to use that to give us some direction. Our displacement is 335.41 meters. Which way? Well, from north, I go this way 26.6 degrees. So I've actually gone east 26.6 degrees from north, and that's how we quote it. We say that this direction is 26.6 degrees east of north. North being the side of the triangle we started from, and we built that angle out to our hypotenuse by heading east. Or as Vine said, eastish. Oh, well, that would be horrendously wrong. No, you're actually totally right. North, east-ish. Because it's not northeast. Northeast is exactly what? That'd be right on this way, right? Exactly halfway between. That is northeast. Between east and north, that's 90 degrees. So what would this angle be in here if it was exactly northeast? 45. We aren't 45, so northeast-ish. If I asked you to give me the direction and you said northeast-ish, I would give you at least a partial mark. I would love it if you could do better and give me the actual degree. Well, I wouldn't accept northeast because it's not 45 degrees, it's 26.7, or 26.6 rather. So northeast-ish is actually better than northeast. It's more accurate because we know for sure it's not northeast. We also know for sure it's not north or east, but we know it's between them. In physics, ish is fantastic. We love ish in physics. In math, ish is bad. But physics is beautiful. We love ish. Okay, questions about what I've just done? Okay, cool. Flip the page. So we're going to look at another one of these kinds of graphs. We're going to see if we can interpret this beast. So we've got a graph. We haven't looked at any of these graphs yet. I'm just throwing it in front of you. This graph is called a position time graph. We've got our 0 right there, and this is the position of a swimmer relative to some 0. I don't know where this 0 is, but that's what we're going to call 0. We have a swimmer that starts 10 meters east of that, and as time moves on, so does the swimmer. The swimmer moves towards our 0, and then if we look at the position, is now west of our 0. At this point, something happens, and then our swimmer starts to move back towards 0, and then east of 0. So let's take a look at how to actually interpret this thing. If we're asked to find the position of a swimmer in any one of these cases, and we're given a position time graph, these things get read right off the graph. So if I wanted to determine the position of the swimmer at 4 seconds, I'm going to go to the 4 seconds on my graph. I'm going to go up to the line because the thing is measuring position. And over, where's the swimmer? What is the position of the swimmer at 4 seconds? Someone say it. Akash, you're taking notes with us, yeah? Yeah, you guys are so quiet. Lena.
8 meters east.
Yeah, it's 8 meters east. At 6 seconds, our swimmer is, oh, yep, 6 meters east. At 10 seconds, our swimmer is 2 meters west. And remember, when we actually, if we're actually going to do math with these things, west doesn't do a great job of plugging itself into an algebraic equation or an algebraic expression. So when we are west, it specifies here that west is negative. So you could say that this is negative 2 meters. So we're clear. At 12 seconds, our swimmer is 4 meters west, or negative 4 meters. And then at 20 seconds, our swimmer is back at 10 meters east. And I'm going to show you yet another way to notate it. You either write the full word or you put the first initial of the word in the square brackets. It's an ominous looking binder. It looks old and full of things.
It might be useful to you for Math 9 or not. I don't
Oh,
know.
absolutely. You gotta. Oh, these are those bad math puns?
Yes.
Oh, I love these. Thank you. Appreciate it.
Ton of stuff in there.
Love it.
You might appreciate it.
Yep, thank you.
You're welcome. What do you use this for?
I make them graph. Well, in our first unit, we were looking at logarithmic graphs. So,
These guys were?
yeah. So I graphed them, we started linear, and we just graphed the points, and we're like, well, what the frig is going on here? Because it's clearly not linear.
Yeah.
So then, actually it wasn't logarithmic, it was, it might just inverse square. And then so it was clearly not behaving linearly, so we brought those graphs out. And then I had them linearize it by rooting everything and graphing it again.
Yeah.
And then we got to see that when we made the linear equation, looking at the root of our length,
Yeah.
this for a pendulum, it actually matched up with if we just read it off the curved graph.
Mm-hmm.
And so we make curves of best fit, and then we're going to find the acceleration due to gravity. I actually make them graph by hand, the displacement versus time graph.
Yeah.
We take tangent lines, they find slopes of tangent lines. They graph those slopes, then they find the line of best fit using that, and then they find it's great.
That's beautiful.
Something you should make your calculus students do at least once. Maybe not more than once.
If you guys are doing that, you are learning.
It's a lot of work, they love it. Well, these guys don't love it yet, they will.
They will.
Anyway, I digress. Those are the positions. Let's find the displacements. To calculate the displacement, what we're looking at is positions between, or positions at one time, positions at another time, and how those positions change. So if I have a time at 6 seconds, or a position at 6 seconds, and a position at 10 seconds, what I want to do to find the displacement between those two things is subtract them, the final minus the initial. So the final position is always the later time. So the position at the 10-second mark minus the position at the 6 second mark. So we're going to actually go through and calculate this thing. Position is equal to, and the way you can write it is, or another way to notate it is, if you recall, that D with an arrow is position, and that is a subscript F that we use to say that this is my final position minus my initial position. The final position is the position at 10 seconds, which we already said was 2 meters west, but for the sake of this, plugging it into the equation, we're going to take west and convert that into a negative. So the position here is going to be -2. I'm going to subtract my initial position at 6 seconds, which was 6 meters east, which is a positive 6 meters. So this is just going to be -2 minus 6, which tells us that in these 4 seconds, the displacement of our swimmer was -2 minus 6 is -8 meters, or 8 meters which way? If this thing pops out negative, then the displacement should have what direction? It should be west. So then once I want you guys crank this thing out, what's the displacement then between 12 and 18 seconds? You guys do this one real quick. When you got an answer, let me know what you get. And I do want you guys to get into the habit of actually showing your work. Write down the equations, plug in your values, get a value. Once you've got it, what do you get? You can also read it straight off the graph too. At 12 seconds, our swimmer's down at -4. At 18 seconds, our swimmer's up at +4. What's the displacement? Sorry, Vine? Did you say something?
No, but it's 8 meters east.
It is 8 meters east, and this is how you do it algebraically. Change in position, or displacement, is final position minus the initial position. Our final position is the position at 18 seconds, which is +4 meters, or 4 meters east, minus, it's always subtraction in here, the position initially at 12 seconds was -4. So it's 4 minus -4, which is +8. If the position is, or the displacement rather, is positive, even if the, well, the position is positive, anything in the positive direction in this case is east. And then we could do the math, or we could just look at the graph. Looking at what we talked about yesterday, what is the final displacement at the end of the swim for our swimmer? It's 0. Why, Vine, is it 0? Yeah, because if your final position and your initial position are the same, you haven't actually been displaced. So the total displacement is 0, because the final position equals the initial position. And what's the total distance swum by the swimmer then? Sorry? Well, the position starts at 10 and goes out to -4. So what's the distance swum here? Goes from 10 to 0 and then 4 more. You said 14? So then he turns, what happens at the 12-second mark? Like, he turns around. He was heading west, and he turns around at this point and heads back to his initial position. So 14 meters out, 14 meters back. Distances only ever add. So 14 meters out plus 14 meters back is a grand total of 28 meters swum. And that's all I'm going to do. Bell's going to go any second now. You have no homework again. You will tomorrow. It's going to be great. We're going to start looking at speed and velocity tomorrow and the difference between those two things. And if you flip again, you're going to look at, yeah, there's a physics land. It's going to be great. Yeah. Are you talking about like kinetic and potential energy? Yeah. Yes. You guys are going to, at the end of that unit, we're going to make a bungee. So we're looking at gravitational potential and spring potential and kinetic energy, and it's gonna be great. We're gonna bring all those things together. So much better than Science 10, because you're actually doing stuff with it. It's gonna be great.
Yeah, and science can be used to paperwork.
Yeah, at the very end of that, we're gonna put it all together, and you guys, I'm gonna put a pool down in the rotunda, and where you guys are gonna get an egg, and you're gonna have to make the bungee. You have to calculate how long you need to make the bungee, and we throw your egg off the edge of the rotunda and see if it survives. Second floor. It's gonna be great. Okay, see you guys tomorrow.